There is a directed graph of n colored nodes and m is. Means there are n nodes and m edges. So the nodes are in colored and edges are given. Okay. So directed graph means there is a direction is how they are connected. Let's suppose for example 0, it is connected with 1 and 2 and there is a direction. The direction is from 0 to 1 and 0 to 2, right? So there are nodes numbered from 0 to n minus 1. If there is n nodes given, right, and the nodes are numbered from 0 to n minus 1, right, should be there. Okay. So you are given a string colors where colors at I is a lowercase English letter representing the colors of ith node in the graph, right? And you are also given a 2D array that have edges, and array at J is A and B, where A and B connects directly connected to each other, right? Means there is a direction S from node A to node B, and the valid path in a graph is a sequence of nodes from x1, x2, x3 and so on till the k, right? Such that there is a directed edge from x1 to x plus 1, and for every I it should be greater than or equal to 1 and should be less than k. The color value of the path is the number of nodes that are colored the most frequently occurring color along the path, and we have to return the color value of any valid path in the given graph, right? What we have to return? We have to return the longest color value of any valid path in the given graph, or -1 if the graph contains a cycle. Okay, so let's understand here what we have given, right? So first of all, if you have observed that, right, what are the things we have given, right? So we are given a directed graph where each nodes has a color like red, blue, green, etc. And your task is to find the maximum number of times a single color appeared along any valid path in the graph. So if there is a cycle in the graph, we will return -1, right? If there is a cycle in the graph, we will return that. Otherwise, we will find what? We will find the largest color value of a given valid path in the graph. Or if there is a cycle, return -1. Okay. So let's read this question, problem statement, right? And after that, go through the example, right? So there is example, we have given example 1 where we have given 0 is having two direction 1 and 2. So 0 is connected with 2 and 1 and 2, and 2 is connected with 3 and 3 is connected with 4, right? Means the color we have given is A, B, A, C, A, and the edges are given like this, right? Each nodes are connected with each other. So let's take this example, and we have a 5 color with the nodes, right? A, B, A, C, A, and the edges are like this, right? So if you represent these edges, you will see that 0, 1, 0, 2, 2, 3, 3, 4 that we have given in the edges, right? Means the path that we have here is how from 0 to 2 and 2 to 3, 3 to 4 contains 3 nodes that are colored in a red color. Means 0, 2 and 4 are in red color, right? Because these are different nodes, but its color are same. As you can see, the one is represented as what? A, then it is represented B, then it represents A, then it represents C, like this. Okay, but these are the colored one are in the red color, and we'll say that there are 3 colors we have in the red color, and so we'll return these 3, right? So the path is from 0 to 3, 4, right? 0 to 3, 4, right? And 3 times we return. So we with the color A having 3 times, and so we return 3 here. Okay, I hope you understand this, right? And how do we solve this efficiently? We can understand here. Okay, so let's understand how do we solve this efficiently, right? We can't do brute force every path, right? Because if you'll go brute forcefully for all the paths, let's suppose there are multiple paths, right? There is only 2 paths, so you are thinking that it's fine, we'll go through this path and then this path, right? But see, a node can have as much as path, right? Because this is a graph, this is a type of graph, right? So a graph can contains many directed graph can contain many you can say edges, right? So if there is a s having between 0 and 1, 0 and 2, there can be many possibilities that there can be a path, right? But if there are too many paths, right, what you will do, right? So we can't go brute forcefully to do every path, right? So there is a key idea, right? So what we will do, we'll use topological sort to visit the nodes in the topological sort, right? So first of all, you should understand what is topological sort in a simple way. So let's suppose topological sort is a way to order nodes in a directed or cyclic graph. You know the DAG, right? DAG is a directed or cyclic graph, right? Such that for every directed edge from u to v, right? If there is a direction from 0 to 1, right? Means let's suppose this is u and this is v, right? So the u comes before v in the order, right? In this ordering, right? So think of it like a scheduling task. If task A must be done before task B, right? Then A appears earlier in the order of B, right? So that is why topological sort is a way to order nodes in a directed or cyclic graph DAG such that for every directed edge from U to V, U comes first, right, in the order, right? Like a scheduling task, right? So what you have to think about that, so you have to imagine if you are trying to take a courses, right? Let's suppose you are taking a courses, right, where you have prerequisites that build software component where one depends on other, right? So you need to complete these things in the specific order so that you can implement the software, right? And that's the topological sort. So the topological sorts having some rules, right? So it will work only on the DAG, directed acyclic graph. There should be no cycle. If there is a cycle, topological sort is not possible, right? So the result is not always unique. It will be different and valid offering maybe exist, right? So you should understand how to perform the topological sort. So topological sort always perform in the BFS, right, approach, and that approach is called Kahan's algorithm, right? So in the Kahan's algorithm, if you know, I'll explain in another video how this works, right? So the Kahan's algorithm, in the Kahan's algorithm, right, you have to calculate the in degree and then how many edges are pointing to each node, right? And how it will start with all the nodes that have in degree equal to 0, means no prerequisites are there, that we will do, because we will start from always here, this one, right? If the in degree is 0, see, in degree we don't have here, right? It is going out degree, but in degree is not here. So we'll start with all the nodes that have the in degree, right? Means there is no prerequisites are there, and then we'll use the queue and we'll pick a node from the queue and we'll add it to the sorted list. And if the degree will decrease the in degrees of its neighbor, all the neighbors, how many in degrees are here, how many in degrees are there, right? Like that we will do, and we'll keep repeating it, right, until the queue is empty. If you were able to process all the nodes, this means that is a valid topological sort. If not, it means the graph has a cycle, right? So that we will do here in this case, right? We'll try to understand how the topological sorts working in this example, and then we will go through. If you're not aware with the topological sort, let me know. I'll create another video for you, and then I will go through this, right? So what I was telling you in the intuition, that we have a key idea is that we will use a topological sort to visit the nodes in the right order, right? Means 0, 2, 3, 4, 0, 1, right? Like that. That is why we will use the topological sort. Because why will start from the 0? Because topological sort will only work where the in degree is 0, right? Means the Kahan's algorithm. Topological sort means Kahan's algorithm, right? Or you can say BFS traversal if you'll do. So you can say, then what we'll do, we'll create a, you can say, color map, you can say color frequency table for each node, and then we'll do how many times each color appears up to the point that we will discuss, right? So that is our thing, and let's understand the approach and other things in the slide. Using that, we are going to we have given what we have given. We have given a graph where each node has a color, and we want to find the path, right, with the maximum number of nodes of any single color, right? And there is a twist. If the graph contains a cycle, we must return -1 because we can't determine a valid path, right? So path can go infinite in the cycle, right? And so we'll return -1 here, right, in this case. Then so this problem is really a combination of what? Detecting cycle first of all in a directed graph. Then we'll use the topological sorting if there is no cycle, and then we'll use dynamic programming to track the frequency of color along the path. So this is a combination of three things in this problem. And so these questions, that is why this question becomes difficult, or you can say hard question of the Leetcode. Okay, so in the short we can say our idea is to solve the problem in an efficient way, and because this will not work in the brute force approach, because we have to go for every path, and that is too many, right? In the, you can say, directed graph, there can be many possibilities, right? In the graph there can be many path will be there, and we cannot traverse all the path, right? And so that the brute force will not work. So what is the idea is that we will use the topological sorting, right, to visit the node in the right order, and then we'll take a, you can say, cloud frequency map for each node, and we'll see how many times each color appears up to the given points that we'll see. But we'll also see how we have to detect the you can say cycle in this graph, and we'll also see if this is not cycle, then we'll go for topological sort, and further we'll check through the dynamic programming, we'll track the color along the path, right? Now understand what are the model approach we are going to use, right? How we are going to approach this problem efficiently, right? So the plan is that we are going to build the graph, and we'll compute in degree for each node. So we'll start with the node that have in degree, right, because we are going to use the topological sort, and then we'll use the BFS, like a FAANG algorithm, to process each node. So for every node we will update its color count by checking color nodes count, and then we'll track the maximum color frequency we have seen, right? If we finish visiting all the nodes, we'll return the max. If not, right, if some nodes are unvisited, right, so there is a cycle, right, and we'll return -1. Okay, so what is the approach is there, right? Just pause this and go through that we'll model the graph using adjacency list, and we'll compute the in degree for each nodes. Then we'll use the FAANG algorithm, and then we'll maintain the frequency count, right, and then we'll store the maximum count, and for every nodes we'll propagate and we'll update them, and further we'll keep track of the maximum color seen so far, and then we'll check if the number of nodes visited during the topological sort less than the total nodes, it means there is a cycle, and we'll return -1, right? Means first we will build the graph, and we'll compute in degree for each nodes. Then we'll start with the nodes that have in degree is equal to 0. Then we will use BFS, like FAANG algorithm, to process each node, and then we'll use for every neighbor, right, we'll update its color count by checking the current nodes value or nodes count, right? And then we'll track the maximum color frequency we have seen so far, and if we will finish visiting all the nodes, we'll return the max. Otherwise, if some nodes are unvisited, there is a cycle, and we'll return -1. Gotcha? So this is the approach that we are going to use here. So what is the algorithm is here? So first of all, we'll build the graph, right? And then building the graph, how we are going to do? First, initialize the adjacency list for all the nodes, and then count in degree for each node. Then we'll initialize two things. We'll check. We'll take a queue for nodes with in degree 0, and we'll have a color count n and 26 to track the max count of each color up to each node. Then we'll we'll use the topological sort, you can say DP. There we'll make a condition while the queue is not empty, we'll pop a node from the queue, and we'll update the global max color count with color count. We'll take u and color of u. For each neighbors u of v of u, for each color we'll go from C0 to 25, and if C is the color of V, we'll propagate color count +1, will increase the count. If the propagates color UV, else we will propagate the color UV, right? And then we'll decrease the in degree of V if becomes 0 add to the Q. Otherwise, cycle detection will check, will maintain a visited count. If visited count is less than n, it means there is a cycle, return -1. Otherwise, continue the answer, right? Means first of all, what we will do, we'll build the graph, we will initialize all the things, right? We'll build the graph, then we will initialize the in degree and the color map. Then we'll go for the topological sort. We'll make a while loop. We'll check the queue should not be empty, pop the first node u, and check its update the global max color at the this map, right? U and the color of u. For each node, you will get the from the adjacency list, you will traverse all the nodes of the u, right? That is called v never nodes. That is never nodes v, and will keep track of all the colors from 0 to 25. If c is the color of v, propagates update its frequency. Else will return u and v, the color, and then will decrease in degree of v. It becomes 0 and will add the q. Finally, we'll detect the cycle, will maintain a visited color. If visited is less than n, we'll return the cycle, and finally we'll return the color, right? I hope you understand, right? So this is the thing that we are going to do in the approach algorithm. Now, if you talk about how will it work, right? So you have the color and these things we have written, right? So longest path will be 0, 2, 3, 4, and the color will be AACB, right? Because the max frequency color of A is 3. Right, so our purpose is that. Let's suppose how it will work, right? So in the graph that we have given, right? So 0, 1. Let's suppose this is it's a 1b, right? Then we have 2a, right? So this is 2a, 3c, and 4a. So this is the path that we are talking about. We got 3 times a. So the time complexity, if we'll talk about, it will come n plus m and 26n. So it will become O of n plus m. And S space 26n plus n plus m. So the space complexity will like. So number of nodes are n and number of edges are m. 26 comes from the number of lowercase English letter, right? So it's time to understand the code, right? So before that, the summary is that we have given a graph where each node has a color, and we want to find the path in the graph where one color appears the most, and we have to return how many times that color appears. If the graph has a cycle, we will return -1. And because the path would be infinite, means color we have given, edges we have given, so the nodes will be like what will map like 0a, 1b, 2a, 3c, 4a, like that we will map it, right? So the first step we will do what is to understand in degree. So a nodes in the in degree means how many arrows are pointing to it. So in the second thing, what we will do, in degree will help us to find whether start the graph, right? Nodes with in degree is 0, means in degree at 0 will say 0. There is no pointing to 0, means there is no in degree is there. Incoming, you can say arrow is not there in the in that node, right? And so that is called that a starting point. Okay. Then further we'll define 1, 2, 3, 4, and all have 1 degree is 1. That is coming from 1 it is coming from 0, from 2 it is coming from 0, from for 3 it is coming from 2, and from 4 it is coming from 3. If you can see here, right, this arrow, right? So in degree for this is 0, but for this one, this is for 1, this is for 1, this is for 1, right? Like that we have to define the in degrees, right? So we'll start with the node 0, right? And then we'll process by node using the queue and BFS, or you can say topological sort. So we also keep track of how many times each node appears up to each node. So at node 0 we'll start. So color is A at node A. So this is the first A. So we'll mark as a 1, and we'll send update to the neighbor, right? That is the 1 and 2, right? So we have started from what? A, right? So there was A, it's pointing to you can say 1, and it's pointing to 2. So we'll update its neighbor. We'll send the update to the neighbor 1 and 2. Okay. Now we'll start from now the start will go to the node 1 where color is B. Will receive A, count is 1, and from 0. And if we will add its B, color B, and B, color is B, and count is 1. Right. So the count for A and count for B is 1. Further we'll go for the node 2 where color is A, right, and gets a color A, count is 1, from 0, will add its own a, so the total count become for a is count 2, right? And will update the neighbor 3. Let's go to the C. After going to the node 3, we'll see color is C, will receive a, count is 2, right? And then from 2 count will become 2, right? Because we have already count 2. Then we'll keep our a equal to 2, we'll add C, so the count will become what? 3, that is a new max, right? We'll send it to 4. 4 will see color is A, will receive A equal to 2, add it to own A, and count, total count is 3, right? So when the total count is 3, we'll check max color count C seen so far. We'll track color count at each node. The highest we saw was with 3 appearing, right? So the final check was there a cycle? No, right? No cycle was there. We have already visited 5 nodes, all 5 nodes, and there is no cycle. So the final answer is the path was 0, 2, 3, 4. We have 3 A nodes, and that is why we are returning 3, right? So let's understand further, guys. But the tips that I'm going to give you is that just imagine that you are walking through a maze in like a graph, and each room has a color flag in a maze, right? As you move, you count how many times you see the same color. You want the path where one color shows up the most, and that is your answer. I hope you understand, right? Let's understand the step by, so you will understand everything, right? So this is your entry point where you will find n equal to colors dot length, right? Means the colors we have given and the edges we have given, as we have already seen, right? Let me zoom a little bit. Okay, so what we have given? We have given colors, and from the colors you will get the n, right? Means we have to find the number of nodes we have given. So number of nodes you can get from the length of the colors string. So this is your entry point, and you have given two things: colors you have given and edges we have given. So colors is in the string, as you can see, and which is a lowercase English letter, and edges we have given is a list of directed edges, right? Now you have the n, that is number of nodes, right? Now we have to build the graph, and the graph should be adjacency list that will store the edges. Then we'll have the in degree, right? So in degree array will index will count, means each element will count how many nodes points into node I. So for all the nodes, right, there should be a count, means this node having count, right? Means how many nodes points into this node, right? Means there was, let's suppose, from 0 u and coming to v, right? So from u to v there is one arrow. Let's suppose more nodes are coming to v, means there can be more possibilities that the count will increase from 1 to 2, 3, 4, 5, like that. So we have to store the in degrees, like we have to store the counts how many nodes points into the node I. Okay, now we will build the graph. To build the graph, we have to compute in degrees, right? So from 0 to n we have graph, we have to add, and we have to initialize all the you can say to add the neighbors, we have to initialize it. Okay, from all the edges, what you will do, you will get the edge and the directed neighbors, means connected nodes, right? You will add, you know this node, right? Then you have the in degree edge at 1 plus plus you will do, so you will increase the in degree for this edge. So at edge at 1, right, there is some there is you can say some value is there, some node value is there, right? Edge at 1, and you are increasing the plus plus, means incoming node. This is the incoming node from 0 to 1. Let's suppose from 0 to 1 we are going, right? So there is a node value, so node at 1, that is called incoming. Understand, right? Means let's suppose there is a 0 node is there, right, and it's pointing to 1, means there is a connection. This is called edge, that is connecting from 0 node to 1 node, right? So one node having only one incoming in degree. So this node have one incoming node, so we'll update this node, right? How? You will get edge at 1, will get this node and will increase its count plus plus, means 1. now have the 1. If it is coming second time, let's suppose there is another points to from 2, right? Means this will come, this will work like how? This will treat it like this. Suppose, let's write another place. Let's suppose from 2 it was coming from where? The 1 first, right? Now it is also coming from 2, right? So either you write this, or 2 times you write like this from let's suppose 0, this or this, right? Either you write this or this, okay, right? So in the graph it will look like this, but it will work like this, okay? Means if you observe this, in degree for 1 is 2 times, in degree for 1 is 2 times. From 0 it is coming from here, and another from coming from here, means 2 nodes coming from 0 and 2 for the in degree. So the in degree for 1 will become what? Plus plus again, so it will become 2, and that is why we have taken the in degrees, right? You understood, right? Means first of all we'll initialize the adjacency list with the empty list for the each node, and then we'll increase, we'll do what? We'll, after building the graph, we'll add the directed edge from edge 0 to edge 1, and we'll increase the in degree for edge 1, right? Like this. Now it's time to use you can say color count. You know the queue, we will build the queue. So the color count is nothing but it will store the max number of colors C from start to node I, right? So if there is a, let's suppose we have some count, right? Color code, right? Color at, let's suppose I. How we are going to store? Let's suppose I'll explain. So at here there is a color. So let's suppose there is I and there is a C. Okay, means we will store at I and C. I is what? Node, right? Node I, and C is the color. So means maximum number of color C from start to node I, right? That we will store here. Means maximum number of color C from start to node I, right? Why? Because there are 26 lowercase English letters, and so we'll take color as a 26. We'll count all the colors, because colors we are representing how? In English letter 26, right? And so for all the colors we'll take 26 as a count here, right? The size. And the I is nothing but the nodes, and you know how many nodes are there? N number of nodes are there. We have checked, right? N numbers of nodes are there, right here. So when we are initializing the color count for each node, so each node become what? N nodes, and the 26 colors are there. I hope you understand, right? You have already initialized the queue for the topological sort. Then we have to start from the we have to start the topological sorting, right? And for that, what you need to do? You have to start from, you have to find, you know the start, right? So you have to initialize the BFS, right? Initialize the BFS and add all starting nodes, that is in degree having 0. So who has in degree 0? You know that, right? So for all the nodes, we'll start from 0 to n. We'll check if in degree is equal to 0. First add all of them into the queue, and its color will be color at this plus plus is 1. We will mark it as its color is 1, because in degree is 0. Means if in degree is 0, we'll mark it as a 1 only, right? Count is 1. Now there is a visited and 0, right? So we have already added all the starting nodes in degree having 0 to the queue, right? And then we'll initialize visited is equal to 0 and result is 0. Means the visited is the count how many nodes we process, and color max color value will be the, you can say, variable that will store the final answer max color value found, and will return it, right? Now we'll do BFS with the topological sort. So let me zoom out a little bit. Okay, here. So first of all, we'll check if the queue is not empty, right? Then we'll poll the first node, let's suppose. But then we'll say visited plus plus, and then we'll find the color at that node. Then we'll do minus, we'll get the color index, right? So the color code value and the color at that node and the color index, if you'll find, if you know that, you will get the count, right? So now you will have the max color value. Let's suppose previously it was 2, now it's 3, right? Just for example I'm saying. So you will get the max color value updated, right? And for all the nodes you will traverse to its neighbor nodes, right? And you will make the loop, and first of all we'll check all the colors. You have to update the color frequency count for the neighbors. You go for all the colors and check the colors, right? How we are going to find the count? You have the color here, count. This is your color and this is your, at this node, for this color, what is the color? Is it matching or not? Then we'll check the colors at caret. This is equal to C. If it is matching, we'll give 1, otherwise by default it will be 0, right? So we'll update its count. If the color matches, count will get increased. And then we'll update our neighbor. This is neighbor node and this is color. So the neighbor nodes and the color you can find from where? The neighbor and the color and the count. Which one is max? That we will update into neighbor, right? So let's suppose it is coming A, then C, and then again A. So we will not lose the number of A count of A. We will not reduce, because neighbor should be updated. Neighbor color should be also updated. 2 times A is coming. So the color for, let's suppose A is coming. What I'm trying to say, the value was A points to color A, points to color C, and then it points to color A. So in this case, let's suppose first time it is coming A, already again coming A. So the color count is 2. Color count is 2. When it is coming C, let's suppose for this I'm saying, right, the color count for this should be what? It should be, let's suppose for C this is coming first time, right? So this is 1, right? But the count is right now is 2, because 2 times A is coming, right? So what should be this count, right? It should be 2. It become, the count will become 2. So if A is coming in the last, again it will get updated to 3, because we have just updated its count. Now count is not 2, now count is 3, because we have checked that if it is matching with the C, we'll get 1, and so we'll update 1 here, plus 1. Again, right? You understood, right? I hope you understand, guys, right? Means what is our purpose is to do, right? For each current node, right? Current node is this node. For each current node, will get its color, right? How will get the colors? You know, right? First of all, you get the current color index, right? And you find the color, right? Then we'll increase the color count node, right? And we'll update the global color, and finally we'll update its global result if the color is max, right? If the color count is max, we'll update the global result if this color count is max, like that we can say. Okay, now we have in degree at neighbor, and we'll do minus, right? Means we are visiting all the neighbors of the color node, right? Means we are visiting all the color neighbor nodes, right? And then because we have already visited, right? So in degree we'll do minus the neighbors, right? So we have already gone through this, right? Here means what we are trying to do, for each color we are trying to propagate max color frequency, right? Max color frequency. And then if the color is the same color, we are adding plus 1 from here, right? And if this is happening, means we are increasing the count, right? Means we are adding plus 1. So if the node has 2a so far, the neighbor is a, right? And so the neighbor has now 3a of as, right? And so we'll update it, that we have told, right? Finally, we have the in degree at neighbor minus minus. We will decrease the in degree of the neighbor. If if uh, if it becomes 0, right? If it becomes 0, we'll do queue dot offer neighbors, and ready to process, we'll add to the queue and we'll reprocess this one. And finally, the final check is that if we will process all the nodes visited equal to n, means there is no cycle. Now we return max value. If it is cycle, return -1. If not all nodes were visited, cycle exists, return -1, right? So as you understand, right? So in this example, what we have used, guys, just think. We have taken the graph, we have gone from the queue, right? We have taken the in degree, then we have traversed all the nodes with the current nodes and its neighbor nodes. Then we have updated the max color code, we have updated the color count, and we have also processed the neighbor nodes having equal to 0. We have processed in the queue, right? Means we have used Kahan's algorithm. We have done BFS plus in degree for topological sort. Then we have tracked the max color frequency from start to every nodes, and if the cycle exists, we are returning -1. If else, will return the max color count seen so far on any valid path. And that's all for this video. Let me know in the comment section that you like this video, and please write time complexity, space complexity, why I have written the time complexity, space complexity like this, and put me in the comment box that you like this video. Thank you for watching. If you found this explanation helpful, don't forget to like this video and subscribe to the channel for more easy to understand coding problems. And if you have any questions, please ping me in the comment box. Please hit subscribe this channel, and please hit the bell icon also, so you will never miss an update from us. And until the next time, keep learning, keep coding. Thank you guys. Thank you for watching.